Hi everyone, welcome to the Flight Engineer YouTube channel, a channel about aviation, technology, and history. I'm your host John, a mechanical engineer with a minor in aerospace engineering, a private pilot in training, and an enthusiast for all things that burn gas or go fast. This video series is intended to be a crash course in the fundamentals of internal combustion engines. I intend to cover a large scope of history, technology, and engineering practice on this channel. However, there needs to be a foundation of basic information available on which more complex topics can be built. I want to discuss the internal combustion engine, or ICEs, in a way that I have not yet seen on this platform. I will talk concepts and theory in plain English, but also show the practical numerical analysis that engineers in the field use. This may become technical at times, but I believe all audiences will be able to gain valuable insights from this and future videos in the series. In the end, I hope this internal combustion fundamentals series will serve as an analog to the ICE classes I took as an undergrad. This first video in the series will start with the background and history of IC engine development. We'll look at the basic components that make up most IC engines, and discuss engine cycles as well as ignition types. Finally, we'll close with an overview of the various systems required for an engine to function. This video covers a wide range of topics at an introductory level only. I have included timestamps throughout so that viewers can skip sections they are familiar with or find sections of interest. Viewers already familiar with these topics may wish to search out future videos in the series to provide more detailed information. These follow-up videos include performance versus durability, which investigates the design trade-offs involved with making an engine that is both useful in its role and reliable enough to be long-lived. Combustion versus detonation will discuss the chemistry and thermodynamic factors of engine operation, including fuels, compression ratio, pre-ignition, and detonation, among other topics. Finally, timing and tuning will look at how various engine systems can be tweaked for optimal performance across its operational range. The internal combustion engine, as we know it today, is the product of countless inventors, mechanics, and engineers working for over 100 years. The first significant advances started in the mid to late 1800s and were pioneered by people like Lenoir, Otto, Brayton, and Diesel. The engines they developed would be hard to recognize as ICEs by our modern standards, but each refined the technology, broadening its application and pushing its successful commercialization. By the early 1900s, fuel development had largely caught up with engine design, evolving from coal gas or flammable dust mixtures to refined liquid fuels that were standardized and produced in large quantities. From there, engine design continued to evolve, producing models more similar to what we would be familiar with today. Since the 1900s, internal combustion engines have become ubiquitous in every part of our modern society. A century of development has seen them implemented in every imaginable application, from transportation to heavy equipment to power generation. The liquid fuels that ICEs burn are not only easily transported and stored, they also possess incredible energy density. The ability to convert this readily available energy into useful work has quite literally facilitated our modern industrial society. Even as new power sources and storage techniques become more prevalent, the internal combustion engine of today will be relied upon to do our most critical jobs for decades to come. A large reason that today's ICE is so critical, aside from its use of liquid fuel, is its adaptability. Designs have branched and evolved to provide useful work tailored to any application at almost any scale. A whole domain of engine designs exists today. They vary in power output from fractions of a horsepower up to tens of thousands, and size ranges from handheld to small apartment block. They use different cycles, fuels, and layouts, among 1,000 other design characteristics, but to begin to understand them, we will look at the basic parts that almost all of them share. We'll begin with the piston. The piston moves in the engine cylinder, creating a closed chamber with variable volume. The piston contains pressure and transmits the force of combustion gases to other engine components. While doing this, it operates in completely linear motion, translating up and down the y-axis in the cylinder bore. The critical dimension of the piston is the bore, which is the outside diameter of the piston or the inside diameter of the cylinder's bore. Next, we'll look at the crankshaft. The crank converts linear motion from the piston into more useful rotational motion for driving vehicles and equipment. It operates in perfect rotational motion. There are two critical dimensions of the crank. The first is crank radius, which is the center-to-center distance from the main journal, the bearing surface at the center of rotation, to the rod journal, the bearing surface at the end of the crank throw. The second important dimension of the crank is the stroke. This is simply twice the crank radius, and it governs the distance that the piston will travel in the cylinder. With the few dimensions we have already defined, we can introduce displaced volume. We can take a look at the piston and crank at the top of their stroke, or TDC, and the bottom of their stroke, BDC. The combination of the piston bore and the stroke length gives us displaced volume of one cylinder using this equation, which is just the area of the circle multiplied by stroke length. For engines with multiple cylinders, overall displacement is simply the displaced volume multiplied by the total number of cylinders. The volume displaced is important because it sets the volume of air and fuel that is combusted in each cycle. Finally, we'll look at the connecting rod. This is the structural link that transmits force between the piston and crank. The connecting rod operates in a complex combination of translational and rotational motion. For these reasons, it's one of the most dynamically loaded components in an engine, but we'll talk more about that in the next video. The critical dimension of the con rod is rod length, or the center-to-center distance from the big end that mounts to the crank's rod journal to the small end that interfaces with the piston's wrist pin. With the main components covered, we can now look at piston motion. We'll use the crank radius A, the rod length L, and a new quantity theta that describes the angle the crank makes with the vertical y-axis. With that, we can derive the following equation with a bit of trigonometry that we won't go into. This piston position S gives us the height of the piston's wrist pin above the center axis of the crankshaft for any given crank angle theta. Now we can observe the assembly's motion and the equation that describes it. Graphing the wrist pin's position over two full rotations gives us the following plot. Here, we can identify that at positive and negative 180 degrees, the piston is at the bottom of its travel, or BDC. Similarly, at positive and negative 360 degrees, as well as 0, the piston reaches the top of its travel, or TDC. In a 4-stroke engine cycle, these segments represent the intake, compression, power, and exhaust strokes. More on that later. Taking the first derivative of piston position, or finding the instantaneous rate of change of piston position, gives us the velocity of the piston over the cycle. Here, we can see that the piston's velocity, when moving down, is highest about 15 crank angle degrees before the midpoint of TDC and BDC. When moving up, it is roughly 15 crank angle degrees after the midpoint. Taking the second derivative of position gives us piston acceleration, and we see peaks at top dead center and bottom dead center, where the piston has to totally reverse direction. Note that the magnitude of acceleration at TDC is almost double that at BDC. These three plots give us incredible insight to the operation of an engine, but they will have to be fully explored at another time. For now, we'll return to our last individual components and cover the block, head, and valve train. From here, it gets difficult to talk about components in general, as the variation in their design, layout, and manufacturing makes them incredibly diverse. We will cover the common aspects, though. The cylinder block, or engine block, is the foundation for an engine and serves as the structural frame for all components. Its primary role is to house the rotating and reciprocating components that we've already covered. The block also provides a means to mount the cylinder head and other engine systems. Commonly, blocks will contain fluid passages for lubricating oil and coolant. Some will also contain integrated passages for intake or exhaust gases. Important dimensions of the block include deck height, which is the distance from the crank centerline to the head deck, and, once again, the cylinder's bore. There are many others, but these are among the most important. Engine blocks have countless layout options, but the basic types are inline, V, or radial. These basic arrangements can be connected, stacked, or otherwise modified to accept as many pistons as the designer requires. Blocks can be fully monolithic, housing the entire rotating assembly, or they can have separate cylinders or cylinder banks. They can have separate main bearing caps, or they can integrate them in a ladder or bed plate style. They can house internal pumps for oil or coolant, or function as an accessory mounting plate for these and other external assemblies. It is all up to the engine designer and the demands of the application. Sitting on top of the cylinder block is the cylinder head. The cylinder head caps off the top of the cylinder, forming a closed combustion chamber in which the fuel and air mixture can be burnt. In most types and layouts, the head will contain valves that lets the intake charge in and exhaust gases out. In most applications, the head shares fluid passages with the block, allowing for full cooling and lubrication of the engine. One notable measurement of the cylinder head is the overall volume of the combustion chamber. This is typically measured with a fluid measurement experimentally or analytically in CAD software. Other notable dimensions include, but are by no means limited to, valve diameters and port volumes. Cylinder heads, like blocks, also come in a dizzying array of variation. 2 valves per cylinder, 4 or 5 valves, no valves, no problem if you're a 2-stroke. You can have 1 camshaft, 2 cams, or no cams at all. All these are common. Additionally, combustion chamber shape and port design are critically important to performance and efficiency. They have to be carefully matched to the engine's other characteristics, so no 2 designs end up the same. As with the block, the wide variability is driven by the designer and the demands of the application. Now that the cylinder head has been covered, we'll make a quick detour and talk about compression ratio. Compression ratio describes how much an engine's intake charge is squeezed after the valves are closed and before combustion takes place. This is represented by the ratio of the charge's volume at BDC to its volume at TDC. To find this practically, we must know the volume displaced, which we covered earlier in the video, and a new quantity called clearance volume, or volume clearance. Clearance volume is based mostly on the combustion chamber, but in reality, things are slightly more complicated. Clearance volume is the intake charge's volume at top dead center. The volume of the charge at bottom dead center, however, is the sum of the clearance volume and the volume displaced. Consequently, this is the general formula for compression ratio. The magnitude of the engine's compression ratio is very important to understanding how it performs, but we'll talk more on that later. Returning to our review of engine components, we'll finish with the valve train. This really isn't an individual component, but a whole assembly or system. All IC engines will have them, but their form and function can vary wildly. Suffice it to say that valvetrains could be their own series of video, but right now we'll just hit the high points. Every engine needs some way to let air and fuel in and exhaust out of the combustion chamber at specific times. Valves, ports, or sleeves, and their many variations, provide this ability. The poppet valve, by far, has become the most common flow control device for IC engines. Because of this, we'll mainly focus on valvetrains that use them. They allow for a metered flow of intake or exhaust gases based upon the linear displacement of the valve, or in plain English, more lift equals more flow. These valves also handle the forces of combustion well, as higher chamber pressures push the valves against their seats, closing them tighter. Actuating poppet valves are the camshaft. This critical component is driven by the engine's crankshaft through a belt, a chain, or a gear drive system, and has a number of lobes that drive the intake and exhaust valves at specific intervals. Each lobe has an eccentric shape, meaning that it is primarily circular, but it has a raised profile somewhere along its circumference used to actuate the valves. The circular sections of each lobe represent a closed valve, while the raised eccentric portions serve to open the valves at critical times. There are many possible arrangements of valve trains with a camshaft and poppet valve. All will incorporate springs that keep the valves closed and pressed against their seats. Additionally, most systems will need a device to turn the cam's rotational motion into linear motion. These will vary in their design, but common designations are tappets, followers, lifters, or buckets. Finally, some systems require a mechanical link to get the linear motion from the cam to the valve where it is needed. This is the job of push rods and rocker arms. Poppet valves are not the only way to control fluid flow in and out of an engine cylinder. The next most common way is to do this with ports, or more simply, holes in the wall of the cylinder. These windows into the cylinder are open and closed not with the typical valve train, but rather by the relative motion of the piston within the cylinder. This arrangement has the benefit of being lighter and more mechanically simple than the traditional valve train, at the cost of some precision and controllability. Cylinder ports also tend to offer better flow than similarly sized poppet valves, but only when fully open. An evolution of the cylinder port concept leads to the sleeve valve design. Engines with this valve arrangement use cylinder ports, but instead of them being open or closed by the piston, an intermediate sleeve performs this function. The piston translates inside the sleeve, which itself translates and rotates inside the cylinder's bore. When the ports in the cylinder's bore align with the ports in the sleeve, fluid can flow in or out of the cylinder. This design combines the flow performance of ports with the controllability and precision of poppet valves. Unfortunately, this comes at the cost of great complexity. This concludes our brief overview of engine components. Next, we'll move on to basic engine operation by covering the most common cycles and ignition types. So far, I have not discussed how fuel and air are mixed or how combustion is actually initiated. The way these steps are performed are key to classifying an engine and understanding how it performs. We'll start with the four-stroke cycle. As a refresher, we can return to the explanation of piston motion. When we plot the position over crank angle degrees and divide it up at each instance of TDC and BDC, you get four sections. These will represent the four strokes of the cycle: intake, compression, power, and exhaust. To understand what is happening during each stroke, we'll focus on the movement of the intake valves, the exhaust valves, as well as the interactions in the combustion chamber. During the intake stroke, the intake valve begins to open as the piston moves down. Charge air, sometimes but not always premixed with fuel, rushes into the combustion chamber as its volume increases. As the piston reaches the bottom of its stroke and begins to rise, the intake valve is just about closed, sealing the combustion chamber. Charge air is compressed as the piston moves upward. Temperatures and pressures inside the chamber begin to rise. Somewhere around the top of the compression stroke, combustion is initiated, either by injecting fuel or igniting a premixed charge. Pressure and temperature in the chamber increase dramatically, pushing the piston downward and doing useful work. Finally, as the piston bottoms out and begins to rise, the exhaust valve has begun to open. The still hot and pressurized combustion gases rush out of the chamber. The upward motion of the piston completes the cycle by pushing the remaining exhaust gases out. While the four-stroke cycle is the most commonly used in IC engines, the two-stroke cycle is still very popular in some applications. For this cycle, we need only to look at 360 degrees of the piston's movement. The piston moving down from TDC to BDC is both the power and the exhaust stroke. The piston moving back up to TDC again acts as the intake and compression stroke. Between the two, there's a transfer step that allows for the whole cycle to work. Two-stroke engines are somehow much simpler and simultaneously more complex than a four-stroke. They are often mechanically simpler, using cylinder ports rather than a traditional poppet-style valvetrain. However, their operation can be complex, as the steps that constitute the combustion cycle seemingly happen on top of one another. To begin to understand this cycle, we'll focus on the interactions in the combustion chamber, at the exhaust port, at the intake port with its one-way valve, inside the transfer port, and in the lower crankcase. We'll start the cycle with combustion being initiated in the upper chamber. Pressure and temperature rise, while burning fuel and air force the piston down. At the same time, the lower crankcase chamber is full of intake charge air. When the piston has traveled some way down the cylinder, its crown passes over an exhaust port, allowing hot combustion gases to escape. While this is occurring, the downward movement of the piston is decreasing the volume in the lower crankcase chamber, compressing the charge air inside. Near the bottom of the piston stroke, the transfer port begins to open. Compressed intake charge air from the lower chamber is forced up into the combustion chamber, where it aids in the removal of burnt gases out the exhaust port. As the piston changes direction and begins to move upward, the volume of the lower crankcase chamber increases. Suction opens the one-way valve in the intake port, and fresh charge air flows in. When the piston is high enough, the exhaust port is covered, sealing the combustion chamber. The charge in this upper chamber begins to compress, setting up for the cycle to repeat. Almost all engines can be classified as either two-stroke or four-stroke, but what is equally as important is the way that combustion is initiated. One of the common methods of ignition is spark ignition. In this system, a spark plug is connected to an electrical source that provides a timed burst of energy. In most spark ignition engines, the fuel and air have already been mixed when the combustion is about to begin. This typically occurs before the intake charge has entered the combustion chamber, but it can also be done in the cylinder during the compression stroke. The electrical source connected to the spark plug creates a large voltage difference across the gap of the plug's electrodes. This causes an arc to jump across the gap, creating an intense, localized heat that starts combustion. The location in the combustion chamber and the timing during the engine's cycle that this arc occurs are critically important for good combustion. The other common type of ignition is compression ignition. This type uses precise fuel metering and the conditions inside the combustion chamber to start the burn. Unlike a spark ignition engine, fuel and air in a compression ignition engine are not mixed in the combustion chamber until the moment of combustion. At the end of the compression stroke, the air in the combustion chamber is at very high temperatures and pressures. Fuel is sprayed into the chamber at extreme pressure, causing it to atomize or separate into small droplets. The small droplets of fuel then spontaneously ignite on contact with the hot charge air. The timing, flow rate, and spray pattern of injected fuel are all critical to good combustion. Let's review the cycle and ignition types by looking at the four most basic classifications of engines. In the upper left, we have the 4-stroke spark-ignited engine. This is one of the most common types and powers the vast majority of cars and trucks on the road in the US. Additionally, this type is popular for motorcycles, recreational marine applications, and most light aircraft. In the upper right quadrant is the spark ignition 2-stroke. These simple and reliable engines power all kinds of portable tools like chainsaws or weed trimmers. They are also a staple in power sports applications, from smaller displacement motorbikes to snowmobiles. Their wide-ranging use meant they were once as numerous as their 4-stroke counterparts, but poor fuel economy and emissions have seen them phased out of many applications. Moving down into the left, we have arguably the most common engine in the world. Compression ignition 4-stroke engines are known for being tough, efficient, and versatile for doing real work. The transportation, agricultural, and construction industries the world over rely on this type specifically. They are also common in road cars outside the US. Finally, we come to the 2-stroke compression-ignited engine in the bottom left corner. This unique type combines the work potential of the 4-stroke compression ignition with the simplicity of the 2-stroke spark ignition engines. The largest internal combustion engines that have ever been built are 2-stroke compression ignition engines, and they're used in critical applications like ocean-going freighters and stationary power generation. Hey everybody, Editor John here. Just decided while I was cutting this video up that it made more sense to leave the engine systems portion as its own upload, where it can kind of serve as an appendix to this introductory video. So thanks for watching so far. Leave a comment if you have any questions on what's been covered up to this point. Like the video if you learned something, and subscribe to see the videos that are coming next. The engine systems portion should already be linked here. And then follow the Instagram to get any more engineering or aviation content from my channel. Thanks for watching, everybody.